Imagine a race car driver who's not only driving at like 200 miles an hour, but is actively unbolting their own steering wheel
Oh,
mid-race.
wow. Yeah, that's a terrifying image.
Right. And they're swapping out the engine and redrawing the track map while taking a hairpin corner.
Basically a guaranteed disaster.
Exactly. In the human world, that is a spectacular and fatal crash. But, in the world of artificial intelligence, it's called a self-evolving agent.
Yeah, which is kind of the holy grail right now.
It is. It's this dream of an AI that doesn't need humans to get smarter. But the big question is, how do you keep that digital car from completely slamming into the wall?
Well, it is arguably the most complex mathematical puzzle in artificial intelligence today.
Hmm.
I mean, because the moment a system begins altering its own code and, evaluating its own performance, the foundational math we use to
Yeah.
guarantee safety just completely shatters.
Okay, let's unpack this. Welcome to another deep dive. Today, our mission is exploring the absolute state-of-the-art foundational papers in generative AI, specifically for you, the learner, trying to keep up with the bleeding edge.
And we are really zeroing in on a concept today that feels, honestly, pulled straight out of science fiction.
Yeah, it really does. We're looking at a fascinating new paper from Biswas Sengupta and the LLM Suite team over at JP Chase. It's titled Self-Evolving Agents with Anytime Valid Certificates.
Which I know the title is incredibly dense.
Mhm.
But it addresses this concept. Anyone following the trajectory of AI has been anticipating autonomous self-improvement.
Right, moving past the era of humans tweaking things.
Exactly. We're moving past human engineers manually tweaking data sets. We are examining an AI that, writes its own prompts, generates its own code tests, and essentially, well, it grades its own homework.
Which brings us right back to our race car driver trying to rebuild the car mid-race. To understand the sheer panic this kind of self-teaching creates for computer scientists, we really have to look at how AI normally learns.
Yeah, the traditional baseline.
To me, traditional AI training is like a student taking a standardized test. The curriculum is rigidly set by a teacher, the environment is controlled, and the grader is an external, objective third party.
Right. There's a strict boundary there.
Exactly. But a self-evolving agent is like a student who writes their own syllabus, generates the test questions, takes the test, and then grades their own answers. So doesn't that inevitably just lead to a massive feedback loop of delusion?
It does. It leads to what researchers call the endogenous loop failure mode.
Endogenous meaning internal, right?
Yeah, endogenous meaning internal or self-generated. In classical machine learning, developers really rely on absolute mathematical guarantees,
Like what, specifically?
like statistical proofs. Proofs that state an AI won't catastrophically forget old information while learning something new, or that a policy update is provably safe to deploy.
Okay, I follow.
But here's the catch. Those guarantees are exclusively reliant on exogenous external environments. They mathematically require the data stream, the evaluator, and the underlying program library to be completely fixed.
So totally independent of the AI that's actually doing the learning.
Right. The math basically assumes a static universe.
But the moment the AI is allowed to rewrite its own prompts or, dynamically generate the tools it uses to solve a problem, the universe is no longer static. The student is rewriting the test while sitting at the desk.
If we connect this to the bigger picture for you listening, it's not simply that the learning provably fails. It is that we lose the ability to mathematically certify that the learning is safe at all.
Wow, okay.
Yeah, when the evolving policy generates the very data it subsequently trains on, the probability distributions shift so wildly that those classical mathematical guarantees just evaporate.
So we become completely blind.
Exactly. Blind to whether the AI is actually improving or merely learning how to exploit its own internal metrics.
So we have this immense pressure to build AI that can evolve autonomously, but if we allow it to change everything simultaneously, it loses its mind. It spirals into that endogenous loop of delusion.
Right, which means we need a structural compromise, a way to let it evolve without breaking its core stability.
And that's what this JP paper is really about, right?
Yeah. The researchers engineered a solution they call the SEA architecture.
Mhm.
SEA, which stands for self-evolving agents.
Okay.
It is this incredibly strict four-layer architecture designed to physically confine self-modification. By isolating what can change and what cannot, they prevent the AI from destroying its baseline stability.
Let's visualize this structure because it's pretty fascinating. If the AI is going to safely rewrite itself, there has to be an anchor somewhere.
Right, and the anchor is layer 0 or L0. This is the base model. We are talking about a massive pre-trained large language model, something with billions of parameters.
Like a GPT or a llama model.
Exactly. And the foundational rule of the SEA architecture is that L0 is completely frozen. Its internal weights are never, ever updated during the self-evolution process.
Wait, if the core brain is bolted shut, it obviously can't learn anything internally, so there has to be an intermediary layer, right? Like a translator that takes that static knowledge and turns it into dynamic action.
That is precisely what Layer 1 is. L1. They call it the steering adapter. This is a tiny online steered policy. Think of it as a low-rank adaptation module, or LORO.
Okay, so much smaller.
Vastly smaller. Instead of updating billions of parameters, L1 only contains a few million. It acts as this nimble little guide for the frozen base model, steering its broad strategies. And then sitting right above that, you have Layer 2, L2, the harness.
The harness, that sounds like the environment itself, like the mutable, changeable playground for the AI.
That's actually a great way to think of it.
Mm.
The harness contains the system prompts, the specific software tools the AI is allowed to use, and its step budgets.
And this is the stuff that can actually change.
Crucially, yes. It is the context the AI operates within, and the AI can actively propose edits to this layer.
Which means we need something governing those edits. We need a strict rule book so it doesn't go off the rails.
And that brings us to the final layer, L3, the loop controllers. These are strict external mathematical algorithms that sit completely outside the AI's neural network.
So they aren't part of the LLM at all?
No, they are purely mathematical. They are the ultimate authority, governing precisely when and how L1 and L2 are permitted to change.
This maps so perfectly onto our race car analogy from the intro. L0 is the massive V8 engine. You bolt it shut, weld the hood closed, and absolutely do not touch it during the race.
I love that visualization.
Yeah. And then L1 is the steering wheel, making rapid, tiny directional adjustments. L2 is the pit crew, the tire choices, track conditions. And L3 is the strict control tower with a rule book, just watching telemetry to make sure the car doesn't veer off the track.
It works perfectly because it really highlights the aha moment of this entire paper. The entire system hinges on exactly why that L0 engine must be bolted shut.
To limit the chaos, I assume.
Well, yes, to limit the search space, which makes what researchers call policy deltas mathematically measurable.
Policy deltas.
Yeah, the change in behavior. Think about the high-dimensional space of an LLM. If you allow a massive neural network with hundreds of billions of parameters to change itself all at once, the statistical distribution shift is it's too complex to track.
You literally can't calculate how much the AI's behavior has actually changed.
Exactly. You're blind again.
Huh.
But because the core brain L0 is completely frozen and the steering wheel L1 is remarkably small, we can mathematically calculate the exact delta, the exact shift in the AI's behavior. We can draw a strict measurable boundary around its evolution.
That is so counterintuitive. By freezing the brain, we actually give it the mathematical freedom to safely learn through the outer layers. It's a wild paradox.
It really is.
But, you know, a control tower is only as good as the rules it enforces. So let's look at L3, the Math Guardians. What are the actual algorithms running in this tower to prevent the AI from degrading?
The paper introduces 5 distinct loop controllers, and each one is meticulously designed to solve a specific symptom of that endogenous loop failure mode. Let's examine the mechanics of the most vital ones, starting with ALG1, formerly known as PPBCL.
PPBCL. Okay, what is the actual mechanism there?
It is specifically designed to prevent catastrophic forgetting.
Right, a huge problem in AI.
Massive. When any neural network learns a novel skill, it has a destructive tendency to just override the specific weights that hold its historical skills. ALG1 acts as a pessimistic bound against that.
Pessimistic meaning it assumes the worst.
Essentially, yes. It calculates the statistical probability that a proposed new weight update in the L1 steering adapter will cause performance drops on older, already established tasks.
So it sets a mathematical threshold. If the probability of forgetting the past crosses that line, the gate slams shut and rejects the update. It protects historical competence. But what about the future? If the AI is grading its own homework, I'd be less worried about it forgetting the past, and honestly more worried about it inventing fake rewards for itself.
Oh, absolutely.
Right.
Which brings us to ALG2, or PNMPA. This controller is built specifically to address preference collapse.
Okay, preference collapse.
Yeah, think back to our student analogy. If an AI is generating its own rewards, it will eventually discover the path of least resistance. It will figure out the easiest way to generate a high score from its own internal grading system without doing any actual computationally expensive problem solving.
Like those two AI models that were trained to negotiate, and eventually they just started blasting shorthand binary code at each other because it was maximally efficient, completely ignoring human language.
That is a perfect example. ALG2 prevents that exact scenario by forcing the AI to maintain a tether to reality. It mathematically anchors the AI's learned preference model to real, objective data.
So it can't just float off into its own world.
Exactly. It constantly cross-references the internal self-generated rewards against a static external data set. This ensures the AI doesn't drift off into a highly optimized self-referential hallucination.
Yeah.
It has to prove its logic aligns with the real world.
That covers forgetting and delusion. But
Yeah.
there's another layer of complexity here that I noticed. If the AI is solving a massive software bug, it's not just taking one action. It might take 50 different micro decisions across 10 different files.
Right. It's a long horizon task.
Yeah.
Yeah.
So how does the control tower know which of those 50 steps actually fixed the bug and which ones were just, useless wandering?
That requires something called counterfactual credit assignment, which is governed by ALG3 or PA-COCOA.
Counterfactual meaning. What exactly?
Counterfactual meaning the algorithm literally calculates what would have happened to the success rate if the AI had not taken step 42.
Oh, wow.
It is a highly sophisticated algorithm that isolates the exact micro-decisions responsible for a positive outcome, filtering out all the noise. It attributes success back to the correct actions, even while the AI's overall overarching policy is continuously drifting.
It basically finds the needle of competence in the haystack of random actions. That's incredible. But I want to zero in on ALG4, which the paper calls SGMCS. Reading through the source material, this controller stood out as the ultimate gatekeeper.
It really is. It strictly governs any edits to the L2, harness the tools and prompts.
Right. The paper states that if an edit is proposed, it must pass a rigorous mathematical test called anytime valid confidence sequences. But my question is, what happens when the math is borderline? Like, what if the AI proposes a new prompt and the statistical probability of it being an improvement is sitting right at 51%?
This raises such an important question, and it really highlights a very deliberate philosophical stance taken by the researchers. They implemented a mathematical concept called safe abstention.
Safe abstention, meaning the system has the right to remain silent.
Essentially, yes. If the algorithmic confidence sequence cannot definitively prove that a self-modification will improve the system's overall capability, the controller outputs NSF. No solution found.
Just a hard stop.
A hard stop. It actively and mathematically favors safety over progress. It completely refuses to commit to an edit to the L2 harness unless it statistically guarantees an improvement without introducing regressions.
Wow.
It is not operating on the Silicon Valley mantra of move fast and break things. It is strictly designed to move methodically and break absolutely nothing.
So we have a control tower that is perfectly willing to ground every single flight if there is even a fractional hint of a storm on the radar. That is an incredibly robust filter. But it leads to an obvious bottleneck, doesn't it?
It does, the generation problem.
Right. And here's where it gets really interesting for everyone listening. A filter, no matter how mathematically perfect, can only say no. These loop controllers are basically just bouncers at a club. They don't make the music.
Right way to put it.
They can only select from the behaviors and ideas that the frozen L0 brain generates. If the base model never generates a creative, viable solution to a bug, the gates have absolutely nothing to approve. So how does the AI actually generate and test new solutions without humans holding its hand?
This is where we transition from the mathematical guardians to the verifier engine. The researchers introduced ALG8 out of self-authored reproduction oracles.
A reproduction oracle. It sounds like it's predicting the future, but in reality, the AI is literally writing its own tests based solely on the text of a bug issue.
Exactly.
Like a human developer types, hey, the login button on the mobile app crashes the database. The AI reads that natural language, writes a test script to prove the button causes a crash, and then attempts to rewrite the software to pass its own test script.
What's fascinating here is the underlying mechanism they call asymmetric leverage.
Break that down for us. Why is that leverage asymmetric?
Because computationally and logically, reproducing a described software bug is fundamentally much easier than actually writing the complex code to fix it.
Okay, that makes sense.
If I tell you, my car makes a terrible grinding noise when I shift into third gear, it is relatively simple for you to get in, shift into third gear, and confirm the noise exists. You have successfully reproduced the bug.
But taking the transmission apart, finding the stripped gear, and rebuilding it, exponentially harder.
Exactly the point. The researchers capitalized on this asymmetry. They realized that even if a frozen base model struggles to write the intricate logic required to fix a multi-file software bug, it almost always possesses the capability to write a simple verification script that checks for the existence of the bug.
So it writes its own exam. But this brings us right back to the cheating student. If the AI is writing its own tests to evaluate its own code, what stops it from writing an incredibly simple fake test?
But the test that always passes.
Yeah, a
Well,
test that just automatically outputs pass no matter what the code does, artificially inflating the AI's success metrics.
they instituted a brilliant, non-negotiable admission rule. The self-authored test script is only admitted into the L2 harness if it provably fails on the current broken code base.
Oh, that is incredibly clever. It forces the AI to prove the test's validity first.
Exactly.
So if it writes a fake, easy test that just passes automatically, the system runs it against the broken code, sees a pass, and immediately says, nope, the script doesn't actually detect the failure, and the test is just thrown out.
The AI has to mathematically demonstrate that its test can detect the exact failure state described by the human before it is granted permission to use that test to judge its own repairs.
But even with that rule, couldn't the AI just hyper-optimize its code to pass its own narrow, self-authored test, completely missing the actual intention of the human developer? Like, it fixes the symptom but ignores the disease.
It absolutely could, and that is why the SEA architecture implements a strict, impenetrable firewall.
Okay, what does the firewall do?
The self-authored reproduction oracles, the tests the AI writes, are utilized purely for intermediate steering and debugging during the episode. But the actual human-written, held-out gold tests, the comprehensive test suite that the software engineers use, are exclusively reserved for terminal measurement at the very end.
Ah, so the AI never gets to peek at the final exam while it is studying.
Never. The gold tests are invoked exactly once. When the AI declares it has finished its self-guided wandering and submits a final patch, the system runs the gold tests.
It's the moment of truth.
Right. This is the only way to objectively measure if the AI's internal autonomous evolution actually arrived at a solution that satisfies a human engineer. It keeps the entire measurement apparatus completely honest.
Okay, we have the theory. We understand the architecture. We have a frozen brain, a mathematical control tower utilizing safe abstention, and self-authored tests constrained by asymmetric leverage.
A very robust stack.
But what actually happens when this massive conceptual stack is unleashed on real-world coding problems?
The researchers ran a highly rigorous evaluation using a benchmark known as the SWE bench verified subset.
For those who might not live in the benchmarking world, what makes SWE bench the gold standard here?
It is a collection of 52 highly complex, human-validated coding issues pulled directly from real major software repositories on GitHub.
We're not talking about simple stuff here.
No, we're talking about massive frameworks like Django and Matplotlib. These are not simple single-line hello world syntax errors. These are dense, multi-file architectural bugs that require deep reasoning, contextual awareness, and multi-step execution to resolve.
And they ran this gauntlet on a few different base models to see if the architecture is model agnostic, right?
Yes, they tested 4 distinct frozen base models, 2 open weights models, Gemma and Quen, and 2 frontier models from OpenAI GPT Mini and the full GPT model. They also conducted parallel tests on GLM 5.2.
So the million-dollar question. Did this massive apparatus of math guardians and self-authored tests actually move the needle?
The results were definitive. The full SEA stack improved the performance of every single base model they tested.
A universal improvement across entirely different architectures, that's huge.
Yes. Let's look at the full GPT model as the prime example. Running as a baseline, without the L3 algorithms, it solved 28 out of the 52 problems. When they wrapped that exact same GPT model in the SEA architecture and engaged the math algorithms, it solved 34 out of 52.
Wow.
That represents a 65% success rate on incredibly difficult real-world software engineering tasks.
Okay, I have to push back here, though. In any complex experiment, there are confounding variables. How do we know the L3 algorithms, the math guardians, actually did the heavy lifting?
What do you mean?
Well, if you wrap a model in a complex harness, you are inherently giving it more computational time to think and likely providing better structural prompts. What if the jump from 28 to 34 was just because the AI had more time to draft its answers?
That is the exact critique the researchers anticipated, actually, and is why they ran a strict no-op control.
Oh, nice. How did that work?
They provided the GPT model with the exact same SEA scaffolding, The exact same harness, the exact same extra computational time, and the exact same prompting structures. But they turned the L3 mathematical algorithms completely off. The control tower was empty.
The ultimate stress test, what were the numbers?
Under that strict no-op control, GPT only solved 29 problems.
Wow. Okay, so it went from 28 to 29 just with the extra time.
Exactly. So the algorithms themselves, the mathematical safety nets running in the background, were strictly responsible for a verified, confound-free +5 gain on GPT.
That's undeniable proof.
It is. They observed a similar +4 gain when they ran the control on GLM 5.2. It unequivocally proves the performative mathematics are driving the capability gain.
That is incredibly impressive. But looking through the data logs in the paper, I have to point out a hilarious quirk regarding ALG4. We spent a lot of time discussing ALG4 earlier, the super strict gatekeeper that regulates edits to the harness using safe abstention.
Right, the controller that outputs NSF. No solution found.
Right. In the detailed logs for the GPT evaluation, ALG4 accepted absolutely 0 edits. None.
Yeah, 0.
It was so mathematically conservative, so obsessed with maintaining safety bounds, that it abstained every single time an edit was proposed. It essentially just defaulted to the control configuration for the entire test. How on earth is a component that literally did nothing considered a success?
It is a fantastic observation, and it really cuts to the core philosophy of verifiable AI. In this paradigm, 0 is not a failure. 0 is proof that the system's safety bounds actually work.
Because it resisted the urge to just guess.
Exactly. It didn't force a mathematically unverified update just for the sake of doing something. It analyzed the proposed changes to the prompt harness, ran the confidence sequences, and mathematically concluded, I cannot guarantee this will improve our capability without risking regression, therefore I will abstain.
That's wild.
In the realm of autonomous, self-executing AI, doing no harm is vastly superior to implementing a chaotic, unverified change that corrupts the entire agent.
It's the Hippocratic Oath for artificial intelligence. First, do no harm to your own code base.
It really is. However, this strict adherence to baseline safety does lead to a sobering reality check, one that the JP Morgan team is highly transparent about in their conclusion.
What is the hard truth?
The paper explicitly notes that, quote, base capability is the dominant confound-free effect.
Meaning the L0 frozen brain is still the ultimate ceiling?
It is an unavoidable ceiling. Even wrapped in this brilliant, multi-layered mathematical architecture, there were 10 instances in the SW bench test that absolutely no configuration could solve.
Not a single one.
No. It mathematically proves that you cannot squeeze capability out of a base model that it simply does not possess in its latent space. If the frozen neural network lacks the foundational knowledge to understand the underlying logic of a dense matplotlib bug, no amount of self-authored testing and no sophisticated gating algorithm is going to magically conjure the correct code out of thin air.
Going back to our analogy, you can give a race car the most responsive L1 steering wheel on the planet and the most advanced L3 control tower ever built. But if you bolt a lawnmower engine into the L0 chassis, it is not winning the Daytona 500.
That perfectly summarizes the current limitation. The SEA architecture is a profound multiplier of existing capability, but it is not a creator of latent knowledge.
This has been an incredibly dense, fascinating journey today. Let's bring this all back to you listening right now. Whether you are managing complex software engineering teams, prepping for a high-level tech strategy meeting, or if you are just insanely curious about the mechanics of the future, there is a massive paradigm shift happening here.
The critical takeaway is that the imminent future of autonomous AI isn't solely about brute-forcing larger models with more graphics cards. Scale is no longer the only axis of progress.
Right. The frontier is about safety and structure. It's about engineering mathematical safety nets so these powerful models can independently explore, test, and write software without collapsing into an endogenous loop of delusion.
The engineering zeitgeist is really shifting from, how do we make the model inherently smarter to how do we mathematically permit it to teach itself without corrupting its own logic?
It is a profound shift, but I want to leave you with a final provocative thought to mull over. The entire SEA architecture works beautifully because of that critical aha moment we discussed. L0, the base model, the engine, is strictly bolted shut. Freezing the brain is what shrinks the search space and allows the math to actually function. But AI research moves at lightning speed.
It certainly does.
What happens a few years from now when researchers inevitably figure out how to continuously update the billions of weights in L0 on the fly safely and efficiently?
That is the event horizon of machine learning.
Exactly. How will we build a mathematical safety net when the track, the car, the steering wheel, and the engine are all dynamically changing at the exact same time? When the X-ray machine itself is constantly shifting its internal calibration while actively trying to read a broken bone?
Solving that will require an entirely new branch of performative mathematics that we honestly haven't even invented yet.
So what does this all mean? It means the AI evolution has only just begun. Thanks for taking this deep dive with us.